Okay, so I'm going to explain this example of integration over a non-rectangular region where we will do it both ways so that you can see the different ways to do it in the y dx or the x dy, but the difference that like in the when using both orders is that in one case you only have to do one double integral, and in the other case you have to do two double integrals. So that's the main idea behind this example. So the function we want to integrate is y squared times x, and the region of integration R is going to be this region between the line y equals negative x, the parabola y equals x squared, and the vertical segment x equals 1. So let's do first the order of integration dy dx, because in that case you don't need to do more than one integral, so you only need one. Let me copy this one more time here, zooming so that it's more clear what I want to do. Okay, so we want to write something like this. Recall that first we're doing the integral with respect to y, so x is fixed. So imagine that you fix a value of x, and as I explained in the previous example, what you need to do is imagine that you use some vertical arrows to describe this region. And so the vertical arrows enter through the equation y equals negative x, and they exit through the equation y equals x squared. Okay? Now, after you can figure out this bound, then you start varying the vertical arrows, and notice that the first vertical arrow can start at x equals 0, and the final vertical arrow is precisely this green segment, which is at x equals 1. So the bounds for x are between 0 and 1. Okay, so let's compute this integral. So you're trying to do the integral from 0 to 1 from negative x to x squared of y squared x dy dx. Again, we're integrating first with respect to y. So that gives you the integral from 0 to 1 of y cubed over 3 times x dx, where you're evaluating at y equals x squared and y equals negative x. So that gives you the integral from 0 to 1 of y to the 6 over 3. X to the 6 over 3. Let me just write, let's pull the 1/3 outside. So you get y cubed, and you replace y with x squared, so that gives you x to the 6 times x minus, so here y cubed, when y equals negative x, you get minus x cubed times x dx. So really this is 1/3 of the integral from 0 to 1 of x to the 7 plus x to the 4 dx. And that's 1/3 of 1/8 plus 1/5. And that's 40, so this is 1/3 times 13 over 40. So the answer that we should get is 13 over 120. Okay, so now what I'm going to do is use the opposite order of integration so that you see where the difference lies. Again, now we want to write something like this: y squared x dx dy. Since you're doing the one in the middle first, or sorry, on the inside first, x is the one that's varying, so y is being fixed. So imagine fixing the value of y. So you're looking at this horizontal segment. Notice that the horizontal segment, right, or the horizontal arrow starts at y equals x squared, but you have to write x as a function of y, so you can say that x equals root of y. So here you put root of y. And then you end at this piece where x equals 1. The reason why you need two regions of integration is that if you had chosen a y that's below the x-axis, right? Notice that it's still true that it exits through the vertical segment, which is x equals 1. But now it enters through the pink segment, which has a different equation. So really what we have to do is separate this into two pieces, like region 1 and region 2. So for region 1, this is a double integral we're computing, but then we have to compute the contribution from region 2, which is a separate double integral. And so here, y goes, it starts at negative x, which means x equals negative y, and it ends at 1. And then, in both cases, I haven't told you the values for y. So notice that if you're using, for region 1, y is always positive, right? It's above the x-axis. It starts on the x-axis, so it starts at 0, and it ends here, which is the value of 1. Okay? On the other hand, on this side, it goes from negative 1, which is here, and it ends on the x-axis. So we're going to compute those two double integrals. The point here is that there were two were needed. So let's see what we get. Hopefully it will be 13 over 120, which is what we found before. And so one more time, when you're integrating with respect to x first, you get 0, 1 y squared times x squared over 2 dy from 1 to root of y plus negative 1, 0 from of x squared, sorry, y squared of x squared over 2 when x equals 1, x equals negative 1, and what we get we integrate against dy. Okay? And so here you get the integral from 0 to 1 of y squared times 1/2 minus y squared. When you square x, you're doing root squared, and so that cancels the square roots, and so you get y over 2. And that's going to be integrated against dy. And here you get the integral from -1 to 0 of y squared over 2, because x equals 1, so you just get y squared over 2, and then when x equals negative y, you get y squared over 2. So you get minus y squared times y squared over 2. That's times dy. So at the end of the day, what we're trying to do is integrate the integral of 0, 1 of y squared over 2 minus y cubed over 2 dy plus the integral of -1 to 0 of y squared over 2 minus y to the 4 over 2 dy. And then this is y cubed over 6 minus y to the 4 over 8 plus y cubed over 6 minus y to the 5 over 10. Okay, these ones are being evaluated at y equals 1, y equals 0, and these ones are being evaluated at y equals 0, y equals -1. And so you get at 1, you get 1 over 6 minus 1 over 8. Here you get, at 0 you don't get anything here, at 0 you don't get anything here, and then you just have to subtract the value of -1. So you get plus 0 minus -1, so it gives you -1/6. And then this one becomes 1 over 10. So let's finish simplifying this. 1 over 6 minus 1 over 8 plus 1 over 6 minus 1 over 10. That gives you 1/3 minus 1/8 minus 1 over 10, which is 80 minus 30 minus 24, right? So this one is 54, and so 80 minus 54 is 26, if I'm not mistaken. And that's the answer that we had found before. So this is an example where by changing the order of integration, you actually end up having to do more work. And I'll just show you an animation to finish this video where you can see the 3D picture of what's going on. So here's an example of a double integral where the region of integration is not a square. So the region of integration here is the region between the line y equals -x, the parabola y equals x squared, and the vertical line x equals 1. So it's almost a triangle, but one of the sides is more like a parabola rather than a straight line. Okay, so on the xy plane, this is where we want to integrate a function. The function that we want to integrate is this one, z equals y squared x. And again, you think of the graph of this function as being a surface. And so here you see the 3D point of view of the problem. So here, again from above, you see the region of integration. And the graph of the surface is like this pinkish membrane. And what you want to think is that you're computing, again from like the perspective of Fubini's theorem, this volume, this integral, as being made up of cross sections, which are these region cross sections that you see here. And as you vary the cross sections, then you get the entire volume. Okay, so I'm varying the cross sections on the right hand side, but you can also take a look at what's happening on the left hand side of the screen. And so as you see on the left hand side, what you're saying is that this region of integration can be obtained out of these vertical segments, which are changing in size. So the difference with the case where the region is literally a rectangle is that in the case of a rectangle, all the segments are of the same size. Here, the segments are varying sizes. Okay, so one way to find the bounds for this region of integration is by imagining that you sort of throw arrows into the region. Okay, and so the arrows pierce this region at different points. So for example, if you throw arrows going this way, they enter through this point and they will move or exit through this other point. But there could be another arrow which enters through this point and exits through this point. But regardless of where they enter, they always enter through the equation y equals negative x, which is why you see this as the lower bound, and they always exit at the equation y equals x squared, which is why the upper bound is here. And then the other remaining bounds that you need to find for the double integral are just the smallest and largest value that x takes on this region. So x can go from 0 to 1, and so that's why we say here that the limits for x are between 0 and 1.